We're about a third of the way through our first Signals and Systems course, and you might be a little confused as to why we're doing all of this. And the phrase I like to use is that it's hard to remember that your job was to drain the swamp when you're up to your butt in alligators. All right. And so it might seem that I've thrown a lot of alligators at you, maybe even thrown you into the alligators, but hopefully we can tie it all together today. So what have we learned so far? We've learned how to create signals out of ramps and step functions. We've learned how to break a signal up into ramps and step functions, or step and ramp. We've learned what how a system will react in the time domain to the impulse, step, and ramp. We've done time domain convolution. And all that is we have a system and a signal, and we find the output signal. And mathematically, our system can be a signal as well. We've also done Laplace transform, or S domain, which is very close to frequency domain, and Bode plots and Laplace kind of go hand in hand. And we've even done rather than using the time domain convolution integral, we use the Laplace transform method. And we've done a little bit of op amps. So why are we learning all of this? Well, that you might think that the answer when you're tired, but really, we need to come up with mathematical models so that we can actually make our lives easier. When you have a mathematical model, you can find the minimum, find maximums, and really do some predictive things to make sure that not everything has to be verified experimentally. And by now you might think, well, why can't I just use LTpsice? And you might say to yourself, well, he would never allow that on an exam. But it's actually more than that. So I thought, really, let's take a simple example of why, although LTpsice I think is a great tool, CAD tools are very helpful. The bottom line is you tell the CAD tool what to do, but the CAD tool doesn't tell you. So let's just say I want to design a circuit that'll make this to be 5 volts. Now I know you know this at the top of your head, but what if you didn't know any circuit analysis? You didn't know what a voltage division equation is. Well, you could build this circuit with a breadboard and just start guessing resistor values and measuring the voltage here until you got 5. LTpsice allows you to make these guesses, if you will. I can step R1 from 1 to 10K with 20 steps per decade, and I can do it with R2 as well. Now, that's a whole lot of guessing, but even so far what we've learned in 110, we can at least make the simulation run faster. So this is a time domain simulation, and notice the voltages are constant. Well, because there's no capacitors or inductors or anything with memory, well then we can run it with a .opt. So I tried it though with a 1 second transient, and I think it took like 78 seconds. I mean, and I actually think it took longer. And even when I'm done, I just can't even use this. I can't even analyze it. So because I see no capacitors or inductors, I can do a .opt or a DC simulation. And so already knowing the difference between static and dynamic can make my life a lot easier, even when using LTpsice. So this simulation took even less than 5 seconds, and it swept R1 here, R2 you can't see, but if you drew a line through here, or saying right across here are your pairs of resistances that will give you the 5 volts. Still kind of a lot to wade through. So even imagine if you had to build this circuit, right? It'd be kind of hard. Well, then what if I asked we need to minimize the power? Well, now you can measure the voltage and the current, change your resistors, So even though let's say you found a pair of resistors that gave you the 5 volts, well, is that minimizing the power? Well, an equation for power of the whole system is given here, and you can see right away that if you want to minimize this power, make the resistances as large as possible, right? That's a great mathematical model to save us time. Sensitivity to changes in R, like what if they're 5%? Well, here's my voltage division equation. What if R2 is as big as it can be, guaranteed? What if R1 is as small as it can be, guaranteed? That voltage will climb to 5.25. What if R2 is as small as it can be and R1 is as big as it can be? The voltage goes down to 4.75. So, the voltage on this voltage divider can swing by half a volt just by using, if the resistors are at their maximum of their specifications. Now it's usually better than that, but you can see that a quick model, rather than having to verify hundreds of experiments and changing your resistor values to see what would happen, it's a lot better to have a mathematical model. Now, what if we're trying to model and filter a heartbeat signal? So I'm not going to explain the whole heartbeat, but you can see that there's some amplitude versus time. And yeah, it looks a little complex, so I'm going to simplify it into actually as a bunch of delayed and scaled ramp functions, which is pretty long right here, right? Because ultimately, what will happen when I put this into a low pass filter, or maybe a high pass filter, or maybe a band pass, or something like that? So even though this is quite complicated, it's a lot easier than the original signal, and should save us time when we're analyzing things. But this is still a little bit much the first time out. So what I'm going to do is just a simple triangle wave. And this is with the idea that maybe this is too simple, but sometimes you have to solve a problem so that you can get to the problem you want to solve. All right, so I'm going to do it two ways. We'll review the convolution integral way and the Laplace transform way. So ht, here's the impulse response. Gt, this is given by this series of ramp functions, delayed and scaled, right? The convolution integral. But I'm going to break it up into 3 parts, because this times RT can be one convolution integral, this times this can be another, and this times this. So I have basically 3 independent convolution integrals. So I'm going to work on this times RT, and then I get a linear times an exponential. That means I have to use integration by parts. I'll post these slides if you're trying to go through that example. But as we go through it, ultimately the first portion becomes t times u of t, which I can simplify as a ramp of here. Then I get another integration over here, evaluate it, and I get minus RC 1 to a decaying exponential. So when I put all that into one function, I have a ramp, I have an exponential decay, and then I have actually a negative DC term. Now the ramp has the ut already in it. This doesn't. This exponential function doesn't. And RC ut needs the step function there. And that's good up until time equals 1. Then I got another ramp function I have to add in. Now, at first I tried to use the convolution integral on that, and it got kind of difficult. And then I just noticed, hey, it's the same ramp function, just times minus 2. So I could scale the previous answer, but then everything is just delayed by 1. So all I have to do is multiply the original function by minus 2, and then anywhere there's a t, I put a minus 1. Voila. And then for r t minus 2, Same thing. I just subtract 2 to delay everything. All right. Not only that, to make my life even easier, I just created a function called lin exponential, linear x times an exponent, where it's the ramp, the exponential decay, and this step function. And all I do is I put t minus 1, t minus 2, scale that by minus 2, and there's my function, right? And you could program it in Python like that very easily. Now, let's do this Laplace method. So basically, I take the Laplace transform, and the impulse the impulse response becomes the transfer function, right? And I'm going to set omega naught equal to 1 over RC, and it just makes it a little bit the transfer function a little bit easier to look at. All right, I have a ramp. I have a ramp with a slope of minus 2 that is delayed, and I have another ramp with a positive slope that's delayed by 2 seconds. So I just multiply everything through, and I get this rather long equation. Again, I'm always trying to make my life easier, and I notice that everything is multiplied by a ramp, but some things are delayed. So really, all I got to do is find out what this is, and then just delay everything else. Well, I have a ramp function times a low-pass filter. In order to do that, I kind of had to do partial fraction expansion because this inverse Laplace transform was not in the table. So this is the cover-up method, and A and C are easily found. B, not so much, and you can look up the cross multiplication method. But basically, I don't have to do it for everything because I already know A, I already know C. I can find B via the cross multiplication method. So just that one part, the first ramp, the output becomes 1 over s minus 1 over omega squared s plus 1 over omega squared s plus omega naught. I take the inverse Laplace transform of that, and I get my ramp 1 over omega naught with my exponential decay times the step function, and minus 1 over omega naught times the step function. When I convert that back into RC, I am left right back with my lin exponential function. So this is just finishing up the math where I pretty much have the same thing as I had for time domain, which is what I was supposed to get. I just went via a different path. Now, the advantage of this path is when you don't have an impulse response that's kind of easy to remember, like the low pass, you can derive the transfer function in the S domain directly. So I verified it in LTpsice. You can download the file from there. And what we have here is the impulse response just plotted out. Here's the triangle waveform. I set RC equal to 0, and V2 is the output of that capacitor, and vcheck 1, 2, and 3 are, I broke up that function into 3, and you can see that it matches pretty well. Some things to notice is that this starts and ends at 0. This response starts at 0, goes up to 1, but then ends very close to 0. So because both things are effectively starting and stopping at 0, the output starts at 0 and ends very close to 0. Now what if we changed RC to be a tenth? Well, now instead of this kind of really blurred shape where instead of this sharp transition it's smoothed out, instead of this sharp transition smoothed out, it actually follows it. There's a little blurring, but then it's almost following it exactly, and there's a delay. And there is something that if this is 2 seconds long and that low pass has an RC constant of 0.1, well, that means the decay time is 5 times 0.1, and so it'll go back to 0 approximately at 2, the original length of the signal, plus 0.5, which is 5 times tau. Here, tau was 1, so the signal was at 2, added 5, and yeah, around 7, it goes back. And notice, RC equals 0.01, right? There's very little, that 5 tau is very small compared to the width of the whole signal, and it's almost matching it completely. And it's actually becoming, the impulse response is becoming like a delta function. Look, it goes up to 1, it's very thin. In fact, the area is 1. Compared to the triangle wave, you can't even see it on the same scale. All right. So with a low pass filter, the smaller the time constant, the closer it gets to an impulse function. All right. What about the high pass filter? It's pretty easy to show, and I've derived it elsewhere, that the transfer function of a high pass filter is S divided by S plus omega naught. Multiply it by that ramp. That S comes out. And then partial fraction expansion is a lot easier. This one's actually, you can look up on the table. All right. And then we get 1 over omega naught, which looks like the exponential response to a step function, but it's scaled by 1 over omega naught. Then we just take, after we take that inverse Laplace transform, we just scale it. I mean, we scale it like we needed to, and we delay it like we needed to. Again, LTpsice file can be found. It's all the same. Now, here the high pass filter RC is 1, and it's still kind of following the shape. Here, the RC time constant is 1/10, and it kind of follows, but then you have a constant slope. And yeah, high pass filters detect edges, and this is an edge with a constant slope, and here's an area of constant slope. Then there's a change, and it exponentially decays to the change, and then here's your constant slope. Now when RC equals 100th, you can't really plot them on the same scale, but notice you get positive slope, negative slope, and very little time in between each area. All right. Then when I made the RC time constant 100, well, actually now I'm getting almost the output again. Now something might be confusing you. V12. Let me go back. This is taking the voltage across the resistor in this configuration gives me the high pass filter, but I only made one simulation, and I just did V1 comma 2 gives me the voltage across this resistor. So it's an easy way to measure the high pass response without making a different circuit. So that's what that V12 is. It's the voltage across the resistor. All right. So now RC is quite large, and now it's almost matching our original signal. So that's some interesting things there. So with the low pass filter, the smaller the RC, the output signal approaches the input signal. The larger the RC, the input edges are blurred and the figure's really smushed out. High pass, smaller RC, the output approaches the slope of the input. The larger the RC of the output approaches the input. Now, that's a great intuitive way to look at things, but man, it'd be nicer to have a systematic way to do that. Well, we're in luck. We have Bode plots. We have the transfer function of a low pass, transfer function of a high pass. Sorry, there should be an S here, but I'm kind of too far into this video to go back. There we go. That's a high pass. And the, sorry. And there's no omega naught. Now, RC in this example equaled 1, so omega naught equals 1. And so it's really, here's V2 across the capacitor, here's V12 voltage across the resistor. For the low pass, this is the cutoff frequency, omega naught. And this is a frequency scale, so yeah, it's about, it's supposed to be 159 millihertz for 1 radian per second. That's pretty close. So here's the thing. If I move omega naught this way, this whole shape of the curve follows along with it. So if I move this point here, that means this follows with it, and it's going to reject more high frequency. When I move omega naught this way, all right, I'm going to allow more high frequency. Now, with the high pass, if I move omega naught this way, that means I'm allowing more and more low frequency. When I move omega naught this way, I'm rejecting more and more low frequency. Well, remember, the Laplace transform of a delta function is 1, meaning something that allowed a signal to pass through unchanged, the Bode plot would just be at 0 dB and 0 phase, constant for any frequency either way. So the more this plot moves like this, I'll just try to, right, if I move this plot like that, well, I'm approaching a delta function, right? If I move this plot like this, right, I'm approaching a delta function. So in the low pass, the higher omega naught, the closer you are to your original signal. In the high pass, the smaller omega naught, the closer you are to your signal. All right. Now, how does this look with our triangle wave? Well, there's something called the fast Fourier transform, and that breaks up any periodic signal into sines and cosines. And so I just ran this in LTpsice, and it's telling me that my wave has a 0.5 hertz component, a 1.5 hertz component, 2.5 hertz component. All right. So if I put my transfer function from radians to hertz, my omega, or my F naught now, is 0.159 hertz, which is around here. So at 0 dB, it's very close to 0 dB at this fundamental frequency of the triangle wave, right? But the thing is these are sine waves, right? So that means I have a sine wave. A triangle wave is not a sine wave. And there's all these higher frequency components. These at 1.5 hertz, I'm out, around here, and the gain is down by 16 dB. 2.5 is around here, and it's even further down. So all these smaller frequencies that are used to make up the triangle wave are getting rejected by that filter. When I make omega naught bigger, I'm capturing more of that data. So just to kind of refresh, right, this was omega naught equals 1 radian per second. And yeah, it kind of gets that fundamental part, but I'm losing all this edge information. Now RC, Thus, RC is going down, omega naught is going up. I'm catching more of that. And I went up by another decade, and now I've almost got the whole signal. With the high pass, I have an RC of 1. It's still almost passing the signal. Then I'm rejecting more and more of the low frequency part, and I'm just getting slope, right? Then when I make omega naught really, really small, I'm getting more and more of the DC part, and I'm almost back to that signal. So that is almost everything to help you understand the first exam. What I didn't exactly do is actually how to construct the Bode plot.